change the order, change the value of inputs, it will get the value will get affected immediately in the value of output on the memory element. It does not depend on the time. Moving on. Okay. Okay. This is known as SR latch. It's a very basic memory element. It is made by cross connecting two NAND gates. It is generally like we mainly use SR latch in making asynchronous circuit, which we are not going to discuss in this session. Okay. SR circuit, as you can clearly see, there is no enable like the clock input to this. So it's mainly used in asynchronous circuit, but we can do some modification and add an enabler like this. Now, in this, if we replace this enable en with our clock signal, then then we have successfully built a SR flip-flop. Okay. Before going to see what a flip-flop is, we are going. It's very much important to see what exactly our clock, because because it's the basic operational like a lifeline to this synchronous sequential circuit. So it's very much important to see what exactly it does and what exactly are they. Okay, like synchronous circuit only employs signal and discrete intervals of time. Like before going to the video, there is a reason why we need stability. Okay, in previous sessions we haven't discussed about the delays in the gates. Like in real world, everything involves gate. Everything has to have some small. We need to give it some time so that after the time instant we give the inputs, it will take a small amount of time before generating the output. Maybe it will be like 10 nanoseconds or 1 nanosecond. Okay, it's 10 nanosecond. It's actually a considerable amount in the digital world. So let's say if one of the outputs in our combinational circuit goes through, like the inputs will travel to 3 AND gate. Like let's say one AND gate will produce a delay of 10 nanoseconds. Then 10 nanoseconds. Like one output will have to go through 3 nanoseconds, and another one will just need inputs have to go like travel through one NAND gate. One output will have a delay of 30 nanoseconds and another one will have a delay of 1 nanoseconds. So at the instant of 1 nanoseconds, only the one value of the output will be correct, and the next and the other value will not be correct because it still didn't get the value from the inputs, like from the gates. So it's very much essential to wait till the 30 nanoseconds so that we will get correct values in both lines. In case if we go and read the values beforehand, like before the 30 nanoseconds time, it will show us error and cause a major malfunction in our circuit we made. So it's essential to wait. And this waiting process is done by including by adding a clock enabler. A clock enabler like enables only when at a particular instant of time. Okay. Now let's see what a clock is. Clock is an it's an periodic wave. I hope you guys are familiar with the sinusoidal waves, which has a periodicity of 2 pi. Similar to that, in digital we only have two values, 0 and 1. So clock goes between only two values, 0 and 1, at a particular in a time period, discrete time period that we define as the clock frequency. Like it forms a periodic train of clock pulse. That's all. Clock is generally denoted by clock or CLK. That's all. And in this diagram, you can clearly see that here flip-flop is the memory element. To the memory element, we are giving clock. That's all. That is how we do it. And where does this clock come from? Okay, in your electronics like gadgets like cell phone, laptops, it mainly comes from CPU, central processing unit. We will not exactly discuss about how they are made. Just we are going to discuss how we use them. That's all. Okay. Now speaking about clocks, how exactly are we going to use it as an enabler? There are three modes of using the clock as an enabler. One, enabling the circuit whenever the clock value is 1, like the entire horizontal line. It is known as response to positive level or a high level response. In this case, the circuit will be active whenever the values of the clock is 1, and it will not be like it will not accept any inputs at the values at the values where the clock is 0. So another two important types of triggering is positive edge response and negative edge response. Now we have clearly see that the clock is in the positive level response, the clock will be active for the whole time where the clock is 1. But in positive edge response, it will be active only in a small interval, like from the transition where the clock goes from 0 to 1. At this particular instant only, the clock will be active. It's like turning the clock on, like turning the flip flop on and off at this very instant, so that we will accept the value of input only at the time instant, and before and after that the clock will not accept any values of input. And it's important to give clock input such that every output values will get stable before before the other clock pulse reaches, like the other positive edge comes. Like in modern day processor, there will be some term known as clock speed, right? 2.3 gigahertz. And the gigahertz is nothing but the speed at which the sequential circuits work inside the processor, or the speed of clock, maximum speed of clock we can work. Okay, negative edge response is just an like opposite of positive edge response. It triggers the clock will trigger our circuit, that is the memory element, only when the transition of the clock goes on. Okay. Hello.
Hello.
Yeah.
Yeah. I have a question. Like we said that in
Hmm.
positive edge triggering, when the signal is going from 0 to 1, the data gets transferred, right? Like the storage element gets accessed.
Yeah. At the one. Okay. Yes. Yes. Good.
So for how long does the storage element will be activated? Like,
Like it's not exactly the storage element being activated. Think it as an gate. Uh, uh, whenever
okay, so
we
it's open for
yeah, it's like an no. The actually the memory element will work everywhere. It's only the input will get transferred. At the activation process is only for inputs, like a gateway. We are closing the gate for the inputs,
yeah,
right? First we are giving a particular value of inputs. It will definitely take some time, right, for every value to settle.
yes.
In meanwhile, we should not allow any other value as an input. So we are
Okay.
closing the gate.
Yeah, and this positive
Okay.
edge response, like in what part of the curve, like the gate is closed, and what part of the curve the gate is open?
Only at the time where it goes from 0 to 1. At the small instant, it opens and closes.
Then, like, what happens when it is kept high for some time? Like that part I'm not understanding.
No. You are talking about response to positive level.
No, no, in the positive
Okay.
edge response itself, like you said
Hmm.
that at that one instant, like the
Okay.
arrow,
You
like
are asking. Okay. You are asking what happens if for clock is equal to 1, right?
yes,
Okay. Clock is equal to 1. Nothing will happen. Like the process will take place. The process of converting, like getting outputs using the gates will take place.
okay,
Like the inputs will be allowed only at that small instant. That like the only at the arrows.
okay,
That's all. And and everywhere else the inputs will not be allowed to get in.
Yes, over that time the processes will be carried out, like
Yeah,
no input
over
will be
that
taken.
one small instant. Yeah.
Okay.
Okay.
Yeah, thanks.
Okay. Negative edge triggering is same to that of positive edge triggering. Uh, the inputs are like allowed only during this small instant where the clock goes from 1 to 0. Okay, moving on. Now we understand, we have seen what's an latch is, and we also discussed about how a clock exactly works and how do we trigger it. Now let's see more about a flip-flop. Flip-flops are the building blocks of memory. It actually stores only two values, 0 or 1. Flip-flops are triggered only during the change in clock pulse. We generally use flip-flop in two modes, positive edge triggering and negative edge triggering. Positive level triggering, we will not use it in most of the cases. Moving on. Okay. It's same positive edge triggering in flip-flop. Like positive edge triggering is represented by the small triangle. You can clearly see that the clock is coming and it's getting inputted to the SR flip-flop here. The triangle symbol tells us that it is an edge triggering. Uh, Edge triggering means positive edge triggering. Normally, we mention positive edge triggering as normal. Negative edge triggering is specified by putting a bubble or a circle before the input to C. Moving on. Okay. Now let's see what's an SR flip flop is. SR flip flop is the very basic flip flop, which is also known as set reset flip flop. Okay. Uh, Actually, we are not going to too deep into the gate level understanding of flip-flop. It will be more complex. So what we will be seeing is that we will just see various values of input and the corresponding values of output and try to create an equation, like try to characterize the flip-flop so that we can use it in our upcoming circuits. Okay, SR flip-flop. Like it will be activated only in case where the clock is triggered. That and all. Okay. Okay. Now we are going to see about what happens to the value of output for different values of inputs. Now consider the SR flip-flop as an, like, you can make analogy with your stopwatch. Like whenever you don't press anything where S and R both are 0, nothing will happen, right? It will just stores the value. If you press like R represent reset. If you press reset alone, the value will get reset. Like it will get reset to 0, right? So the value stored, like the Qn plus 1 is the next state value, and Qn the value that is stored, like presently holding. Like it will be resetted to 0. And if we set the value to 0, we will generally setting the value, some value of time rate, 60 seconds, 120 seconds. But in digital, we only have two values, 0 or 1. So we will set the value 1 in case we are only pressing yes. And in case we press both, actually in clock, we don't like in stopwatch also, we don't press set and reset at the same time, right? It will show some error, like every LED segment will get lit up and show some error. Similarly, in this circuit also, it's an error condition. We'll discuss how to overcome this error in coming part and how to use this error for our benefit. Now you can clearly see that like whenever the clock is like 0, 1, under the clock column, there are values like 0, 1, 1, 1. Actually, this 0 does not represent the exact value of clock. 0 here represents the untriggered state, and 1 represents triggered state. Please note it. Okay, whenever the clock is not triggered, whatever value of S and R we giving it, we are not allowing the inputs to come in, right? We are the gate is closed for the inputs, so it will not come, and the value will remain as it is. More like an storing. and whenever in the the rest of the all cases will only be activated, and only the values will get manipulated in the state where the clock is triggered, where all these cases where SR is 00, 01, 10, 11. Moving on, this is the characteristic table for SR flip flop. As I mentioned earlier, whenever S and R are 0, 1, the value like R is 1 means the reset rate. So we are going to put 0. Whenever S is 1, we are setting a value. We only have two values, right? 1 and 0. So we are setting 1. S and R both are 0 means nothing will happen, and the previous value, the present state value Q, will be directly stored there. Similarly, if the present state value is 1, 1 is directly stored here. Nothing will change. And 1, 1 is an invalid case, so we are not going to discuss about it. And in this case, the X represents that whatever value, it does not matter, right? Whether Q is 1 or Q is 0, if R is S is equal to 0 and R is equal to 1, the output will be directly 0 and 1. It does not depend upon the value of Q. As you can see here, whenever in these cases 0, 1 and 1, 0, it will always be S is 0 and R is 1. It will always be 0. It does not depend on the value of Q. And similarly, 1, 0 case, it will be 1 irrespective of the values of Q. The Q value, the next state value depends only on Q in these cases, where both are 0, 0. Moving on. Okay, now we'll do simulation in logism with SR flip flop. Okay, the screen is visible, right?
Yeah, it is visible.
Yeah, okay. Okay. You can find the flip flops, all type of flip flops under the section memory. Drop it down, and you can see SR flip flop. Pick it up and place it there. Okay. Okay, I'm zooming it a little bit. Now you can clearly see there are outputs like this is S or set reset pins. This is the value of Q, and this is the complemented value of Q. And this small triangle, as I mentioned earlier, represent positive edge trigger clock. Now, now we are going to get a clock. For getting a clock, it's go to the wiring and drop it down. There will be a clock. Take it and place it here. Connect the clock and take two input pins for S and R. And we are going to have a digital oscilloscope to see what exactly happens whenever, like, you guys had doubt, right? Like about how exactly the clock works. We are going to see. For that, go to the input output extras, drop it down. Under this, you will have many components. Go and pick up press the digital oscilloscope. Take it and place it here. And you can go and change the number of inputs it has. We're planning to give 2 inputs, so go change the number of inputs to 2. Okay. Now this is the digital oscilloscope. We are just using it for illustrative purpose. Don't worry too much about what it exactly does. Okay. Now there is a small triangle symbol, right, which represents the clock. So we need to give the same clock to this thing. Okay, we connected the clock, and now we are going to connect the value of Q to the one input. What exactly the digital oscilloscope does is it generates wave, depends on the value, input value we are giving. Now, to turn on the clock, we are going go to simulate, and under the simulate there will be an option called auto tick enabled. Click that. Now the clock will get activated, like it goes to up and down, like it goes to 0 to 1 rapidly, right? See, periodically it goes from 0 to 1, 0 to 1. It moves. Oh, this is the clock pulse. Also, we can go and change the frequency in which the clock is, like the clock pulse we are providing. Like it's now in 4 hertz, we can slow it down to 2 hertz. It's slow down. We can also put whatever values we want, like C 16 gigahertz will be very fast, and 2400 gigahertz, like 2 megahertz means will be super fast. Actually, this is the frequency in which our computer processor and all will work. In case you guys are familiar with the RAM speed being 3200 megahertz and processor speed being 2 or 4 gigahertz. Okay. For our simulation, we are just sticking to the 2 hertz frequency range. So it will be better to see with our human eyes what exactly it happens. So as I mentioned earlier, now both S and R are zero. What 0 means? It's in memory state, right? 0 will remain 0, does not change. So the Q value does not change, doesn't change. So it will be a small line just going through zeros. If I go and change the value of S, it's a set, right? Set, and I'm taking my finger from the button. Now the value will be 1, and the value remains 1 because we again put the values to 0, right? Like pressing it and leaving, taking the hand back means it will goes to 0. So the value is in memory state. So the value of Q like remains 1 as long as we are keeping the values of input to 0. If I go and press the value reset to 1, see what happens. It will again goes down to 0, right? See. And I'm also now taking my hand from the reset button and again setting the values. Now go stop the simulation. Okay. As I mentioned earlier, okay, as I mentioned earlier, see the value changes only when the clock pulse goes from 0 to 1. See the 71st clock pulse. The value changes from 0 to 1, and while it's going down, it doesn't changes. And for the next clock pulse, 72, it doesn't changes because our state is in 0. We change our state only when the clock goes from 0 to 1. It's affected only there. This is what I meant by positive edge trigger. Okay. This is the SR flip flop. Now, okay, is the simulation clear? Are you guys okay with it?
Could you explain the working of SR flip flop once again, like changing the inputs
Yes,
and
sir.
outputs?
Okay. Okay, I will do it. I'm resuming the simulation, and okay. Now 0 is memory state, right? See, whenever the both S and R are 0, the clock will be in the memory state, which means it does not changes. 0 means just value will not get changed. Similarly, see, I'm keeping the both values in 0. and the clock remains at 1, right? See, sorry, not clock. The value of Q remains at 1. See, does not changes.
Yes.
If I go, okay, if I go and set the value to, okay, the value is already 1 year. I'm now going and resetting the value. At the instant I press reset, see, it goes to 0. And it remains 0 because it's rapidly changing. Because the reset being 1 means it's always 0. But it remains 0 even if I turn off the reset, because both are 0 now, which means it stores the value, does not change the value, right?
Yeah.
Okay. Now you can go ahead and check, like set the value again. I press yes again, it becomes 1, right?
Yes.
And also see that like even if for example, even if I press the button, like I pressed yes in some time, right? Even if the time lies somewhere between 58 and 59, like sorry, 59 and 60, it does not change immediately. It waits for the next pulse, next past stage, where it goes from 0 to 1, and it changes only there, right? Does not change in anywhere else. See,
Yeah.
in the start of 60 only, it's in the start of the clock pulse 60, where it goes from clock pulse goes from 0 to 1, the value of Q is changing. And
Yes.
yeah, that's all. At the time interval only, we are allowing the inputs at a small instant, triggering. Use the term trigger.
I
See,
was confused with the gate diagram for this. In the gate diagram, like not as a block diagram, but as the gate diagram.
yeah, it's better to see it as block. You don't
Okay.
be using the gate diagram in great details.
Okay.
Yes, or flip flop. Okay. Now, even if I go and change the value to like to 0, it will remain because of the memory state. It will not change the value. So, okay. Are you guys clear with SR flip flop? Is it okay? If you guys have doubt, you can unmute and ask. Okay. Let's go to the next topic. Actually, the state table is nothing but an expanded version. We are speaking about all possible cases of Q, S, and R, and corresponding values of Q n plus 1. Like every case is 0, 0, 0 to 0, 0, 1 up to 1, 1, 1. We're discussing every cases, and corresponding to that case, we are telling whether what's the value of Q n. In the case where both S and R are 0, it will retain the value. Like since the value present here is Q, the Q will be transmitted here. See, in this case 0, 0, it go check the value of Qn, and Qn value will be given to Qn plus 1. Does not changes. And in set case where S is 1 and R is 0, S is 1 and R is 0, the value will be 1 irrespective of the values of Qn. See, it will be 1 in both cases. Similar goes for 0, 1, reset case. The value will be 0, 0, irrespective of the values of the Qn. See, in this case, Qn is 0, and in this case, Qn is 1. But doesn't matter. Doesn't matter. Whenever we press 0 and 1 for S and R, it will immediately become 0. And S1 and R1, it's an invalid case, so we are not doing it. Now, moving on to the very simple and very easy looking flip flop, D flip flop. D flip flop will be more useful. Even if you guys don't understand SR flip flop, don't worry. SR flip-flop is basically for building other flip-flops. We mostly don't use them in our circuits. We'll use flip-flops like D, JK, and T. Especially D is very useful flip-flop. D flip-flop, often the value D, like D is an full form of D is for data. This flip-flop specializes in storing data. It, as you can clearly see, it's more suited for operations involving memory storage. It can be made easily by giving complement of S to R. Okay, what does it exactly mean? Okay, in SR flip-flop, there are cases we are in D flip-flop, we are going to avoid the case where both S and R are 1. Right? Giving a complement input. Like whenever S is 0, we are making sure that R is 1. Whenever the S is 1, we are making sure the R is 0. We are doing nothing. We are just giving input value to S, and the same input value is given to R by connecting a NOT gate, so that these two cases are not possible. Like the 0 0 case and 1 1 case are avoided. And D flip flop only uses these two cases, that 0 1 and 1 0 case. That's all. As you can clearly see, we have an input terminal, a clock, a triangle representing its and positive edge trigger, Q and Q bar for output, and the output which is inverted. Okay. Now, as I mentioned earlier, D0 means S is 0 and R is 1, because R is in complement of what we give to S, right? Now, in that case, S0 R1 means what? It's a reset condition. Reset means the value will gets 0 input. Like we will store 0. We will put 0 for that value. In case where D is 1, it's in case where S is 1 and R is 0. S1 R0 is the set. Like we are setting the values. So it becomes 1. It does not depend upon the value of Q. So we have characterized the equation, like characterized the flip-flop using this equation, where Qt plus 1 depends only on D. See, the RHS does not have any dependence of Q. You can see the, like, it does not depend. You can clearly see it from here, right? Q only depends upon D, does not depend upon the value of Q. Now we are going to going again to the logism and simulate and show you guys what how it works, the flip flop. Okay, and I'm opening a new circuit. Again, go to memory. Under memory, the first flip flop given is D. Take it out. We only have one input in this case, because we are giving one inputs to S, and the same input is complemented using NOT gate and given to R. So we are taking one input terminal. Again, the clock. We are placing the clock. It's a positive edge trigger. Also, I forgot to mention one more thing. If you go and click this flip flop, it's possible to change whether it's a rising edge or falling edge. Please don't use the high level or low level. High level, low level, we don't use. It does not like. It is not very useful in our simulations, like in our circuits. So we generally use two cases: rising edge trigger and falling edge trigger. Now I am setting the value to rising edge trigger, the default value. Again, we are now going to add the digital oscilloscope. Again, only one value is enough, one input value. We need to connect it to clock and connect the output from flip-flop to as an input to the digital oscilloscope. Now go to simulate. We are going to activate the clock. Click auto tick enabled and set the frequency you want. In this case, like, 2 will be enough. So we can see it clearly what's happening. Okay, now see it clearly. Our input is 0 here. What will happen if the value to like the value the input value is 0? What will happen? The output value is 0. The value with next state value, the Q value is 0. See, the value is 0 throughout. Whenever I go and press it to 1, it becomes 1. And it becomes 0 whenever I take my hand, like not pressing it. See, in D flip-flop, we don't have a concept of memory state. Memory state can be only achieved using clock by turning off the clock or by enabling the flip-flop. See, it's a very simple looking flip-flop. 0 here means 0 here, nothing else. If I press 1, as long as the value is 1, it will be 1. And again, when I'm going and pressing, turning it back to 0, see, it becomes 0 in the next immediate clock pulse. Turning it on and turning it off. Now I'm pausing the simulation. Now see. Now see, the value changes only at positive edge triggers. See, at the 95th clock pulse, the start of the 95th clock pulse, where the clock goes from 0 to 1, the value is changing. Even let's say I press the I press the button exactly at some time between 94 and 95, but it does not change immediately. It waits for the next clock pulse because it's for the edge trigger, positive edge, because it is the time only time where we are allowing the inputs to go to the flip flop, and it waits for the clock pulse. Only then it changes. And let's see. In this case, I again change my value of D from 0 to 1. Let's say some point between 98 and 99, I press it back to 0. It does not change immediately. It waits for the next positive edge trigger. At the next positive edge trigger only, we are accepting the values of inputs. So at that point only, our value of output changes. I hope it's clear to you guys. If you have any doubt, you can unmute and ask. Okay, do you guys understand a D flip flop? If so, please write yes in the comment so that it will be understand whether you guys understand or not. Thank you. Okay. Now let's see what the characteristic equation. Like characteristic equation is nothing but all positive values of D and Q, 0, 0, 2, 0, 1, 1, 0, and 1, 1, and the corresponding next state values. See, see the truth table of D and Q of T plus 1. Both are same, right? 0, 0, 1, 1. See, 0, 0, 1, 1, which ensures that this equation holds true. Both are equal. Does not depend upon the previous state value. Does not matter. Whenever I press 0, it should become 0, even if it's 1, the previous state value is 1 or 0. Same goes for D is equal to 1. Whenever I press 1, it should change to 1. It should not depend upon whether, like, it doesn't cease, right? Uh, Irrespective of what the value, 0 and 1, both cases it becomes 1. So it does not check this value. That's the specialty of D flip flop. Very simple. The only thing you guys need to remember is this characteristic equation. Besides that, we can build anything using this characteristic equation. Just remember characteristic equation. That's enough. Okay. From JK flip flop, Delia will continue. Delia, over to you.
Yeah. So good morning, guys. I'm Delia, and I'll be teaching you the flip flops. Can you see my screen?
Yes, it is visible.
Yeah. So as Irwin explained you what SR flip flop is, let us see what JK flip flop is. So JK flip flop is very similar to SR flip flop.
Delia,
Only yeah.
hello. Can you continue after 5 minutes? Like participants are requesting a break of 5 minutes.
Yeah. Okay. Fine. Let's start at 10:15.
Yeah, okay.
Okay, let's start, guys. Yeah, so can you see my screen? Hello?
It's black. Okay, now it's visible.
Okay. Yeah, so as Irwin explained you what SR flip-flops are, JK flip-flops are very similar to SR flip-flop. Only the thing is, when in SR flip-flop, when both S and R are was equal to 1, that was an invalid case because you can't have set and reset simultaneously. In JK flip-flop, if you have J and K both as equal to 1, you will see the toggling. There will be a toggling again and again, or or you can say racing. Let's see the truth table of JK flip-flop. See, when the clock is 1, when the clock is 0, and whatever with the maybe the value of J and K, the next state will be equal to memory or the previous state. When clock will be 1, uh, if J and K are equal to 0 and 0, the next state will be equal to Q1, that will be the previous state or memory. When it will be 0 1, it will be 0. When it will be 1 0, Q1 plus 1 will be 1. And see, when J and K both equals 1, it will toggle. When both will be 0, it will be memory. When both will be 1, it will toggle. Toggle in the sense it will be the complement of the previous state. Now looking at the characteristic table, a characteristic table is nothing but when you have Q1, JK and Q1 plus 1. So as you see, as J and K equal to 0, we saw that when J and K equal to 0, the next state will be equal to memory. So similarly, when J and K both are 0, Q1 plus 1 will be same as memory, which is Q1. When J and K is 0, 1, you will have 0. So wherever you have J and K as 0, 1, J as 0 and K as 1, the next state will be 0. See here also, when when J is 0, K is 1, you'll have next state as 0, irrespective of whatever the value of Q1 be. When you have 1, 0, when J is 1 and K is 0, the next state will be 1. Similarly, when it does not depend on Q1, when you have J as 1, K as 0, Q1 plus 1 will be 1. Now, let's see what happens when both of them are equal to 1. When J and K, both of them are 1, first it will toggle. Okay, so Q1 is 0, so it will toggle to 1. And over here, when Q1 is 1, it will toggle to 0. So this is what characteristic table is. Now let us see JK flip-flop in the logism. Okay, can you see my logism window?
Yes, you can see.
Yeah, so into the drop-down menu of memory, see, find for a JK flip-flop and just put it anywhere on your screen. So this is clock. Okay, so like take clock from the wiring drop-down box, place it somewhere. take the input pins for J and K. Let's use digital oscilloscope. You'll find it in the input output extra. Reducing the number of inputs to 2, or let's say 3. Okay, let's reduce it to 2. Join the clock. Okay, let's join this Q. And so what is this? This is nothing but complement of Q. Whenever you have a bubble, that means the complement. So here, if this is your next state or the present state, whatever, the output, this will be the complement of that. Yeah, so as you see, as soon as the clock is moving, your Q, when you have J and K as 0, Q is equal to 0 and the correspondingly Q prime will be equal to 1. Now let us change J to 1. Yeah, let us change J to 1. See, what do you find is, as soon as you change J to 1, so let us go back to the truth table. See, when J is 1 and K is 0, the next state will be equal to 1. So when J is 1, K is 0, you find Q, which is the next state, will be equal to 1 and correspondingly, thing. Yeah, so when J is 1, K is 0, you'll have next state as equal to 1 and correspondingly its complement will be 0. Now changing both of them to 1. Say it toggles. Q toggles and therefore Q prime will toggle complemented to that. Let's stop this simulation. Yeah, so is JK flip-flop cleared? Put it in the chat. Is it clear? JK flip-flop. And like what is the characteristic equation for the next state? So if you want to find a characteristic equation of the next state, which is qn plus 1 or qt plus 1 in terms of j, k and q, just make a k map using this and you'll get the equation as this, which is jq prime plus k prime q. Now let's move on to the T flip-flop. Now what is T flip-flop? T flip-flop can be made by connecting J, for instead of giving a different output for K, we'll give the same output as J. So by connecting J and K, we'll get the T flip-flop. So what is the use of T flip-flop? It will just toggle. It is used to toggle. And like T flip-flops are generally used in a circuit which involves the counters where we need the toggling. Okay. So let's see what is the characteristic table of T flip-flop look like. So whenever, like if this is a present state and this is a toggle, like this is the input basically. If it is 0, you won't get any toggling. You will get the next state will be same as the previous state, or that will be a memory. When you put the toggle on, or when the toggle is 1, you will get it won't depend on the previous state. But like putting a toggle as 1, the next state will be the complement. It will be the complemented of memory. So the characteristic equation of q of t plus 1, that is the next state, will be XOR of t and q of t. So you'll get this as t XOR q of t. For t is equal to 0, it is a memory state. As you can see from the characteristic table, whenever t is 0, the next state will be same as the previous state. So that is a memory state. When t is equal to 1, it is in toggle mode and the value gets complemented. State table will represent all values of t and basically it is an expanded form of this table wherein you will consider each and every condition. Okay, so like whenever toggle is, if you have t as 0, q of t as 0, so it won't toggle. It will be same as the previous state. Whenever the toggle is, t is 0, like toggle is 0, previous state is 1. The next state will be same as the memory. Okay. When you put the toggle on, when t is 1 and the present state is 0, you'll get a complement of q of t. So complement of 0 is 1. So the next state will be 1. Similarly, this is 1. So the next state will be the complement of the present state. Now let's see the simulation of T flip-flop. So you'll find T flip-flop in the memory drop-down. Just select the T flip-flop. Yeah.
Table, madam.
Yeah.
Only whenever one condition is there, then only the competitive output will be there, madam. Only that one T that particular condition only the complementary will be the output, right?
Yeah. When
Okay,
T will
okay,
be 0, you will get the value. The next state will be the same as present state. And when T will be 1, you will get the complement of the present state.
okay, madam. Okay.
So the value will toggle between 0 and 1. Okay, so yeah, take a T flip-flop from the memory drop-down and put it on your screen. Yeah, so here let's not use digital oscilloscope. Let's see what happens. Let's use the normal output. Yeah. And yeah, so see, whenever the input is 0, that is whenever the toggle state is in 0 state, and when you change the clock, you will see that there is no change in output, it is 0. So basically it is not toggling. Whenever you put the toggle to 1, change the clock, you will see it toggling. You will see the output as toggling. Can you see? So basically when t is 0, whenever the input to t is 0, as soon as the clock goes forward, the Q will be same as the previous as the present state, so it won't toggle. Whenever toggle is 1, you'll see that this toggles. This is what toggle flip-flop is. Now let's move on to some examples and simulation. Yeah, so as Irvin explained you about the D flip-flop, this was the excitation table of D flip-flop where D was equal to Q of T plus 1. You can see from this table, from the excitation table, that the values of D and Q of T plus 1, that is the next state, are same. So it represents a D flip-flop where the next state is just equal to D, which is the input. Now we are going to make a sequential circuit using a D flip-flop. Consider this as a characteristic table, okay? And you need to design a sequential circuit using a D flip-flop. Now here, like, we don't have any output, right, given. So we'll consider Q of T, like Q of T as the output. Yeah. So like we'll add like one more table as D. What, as we know that D is just equal to Q of T plus 1. We are supposed to design a sequential circuit using a D flip-flop. So D will be equal to the Q of T plus 1. We know this from the excitation table of D flip-flop. Okay, so the truth values of D will be similar to those of Q of T plus 1, as you can see from this table. Now let us find D as a function of what will be the Boolean equation of D in terms of Q, X and Y. Okay, so we'll make a K-map for this. 3 variable K-map, and let's take a variable Q on this side and X and Y over here. So as you know that this is 0th, this is first, this is second, and this is third, fourth, fifth, sixth, and seventh. Putting the values correspondingly, you'll get this as a K-map. Now here you can see you can't pair any of the ones. So writing them, you'll find this one can be written as q prime x prime y. This can be written as q prime x y prime. Similarly, this can be written as q x prime y prime, and this as q x y. So this is what is the Boolean equation of D in the terms of q of t, x and y is. Okay, now let us reduce this. How to reduce this equation? If you take q prime common from these two terms, from the first two terms, you will find q prime into x prime y plus xy prime, which is nothing but, which is a Boolean equation for x or y. So you can write this as q prime into x XOR y. And similarly, taking q common from these two terms, you will find x prime y prime plus y xy. This is nothing but this is x nor. So the whole equation can be written like q prime into x XOR y plus q into, this will be x nor. I mean, this will be complement of x XOR y. Okay, so this can be written as q into x XOR y, a whole complement. Did you get this? Any doubt in this? Okay, so basically you just have to use this identity, which is x XOR y, which is equal to xy prime plus x prime y, and the complement of this is equal to x prime y prime plus xy. Using this, you'll get D as x XOR y XOR q. Now let us make a circuit in logism. So you need a D flip-flop. Okay, let's first. So we need D flip-flop. Let's place it on the logism screen. What is the equation? X XOR y XOR q. So you basically have two inputs as x and y, and q will be the memory. You'll find XOR gate over here. Just place it. So you can see like one of the input is to the final XOR is q. So let's take a memory from q, feedback from q. You can see from the equation we need two XOR. The final XOR will have q as one of the input, and the other will be x XOR y. So let us take one more XOR get, which will have input as x and y. Okay, so this is X. Let's say this is X, this is Y. You'll get X XOR Y. Then this is D. So over here, you'll get X XOR Y XOR D as an output at this place, which is equal to D. Now let us put clock. And as an output pin, yeah, now let us simulate it. Let's go to the truth table and see. See, when X and Y are 0, you'll get D as 0. When X and Y are 0, you'll get D as 0, okay? Now putting X as 1 and Y as 0, the next state or D will be equal to 1. So you can see that this will follow the truth table. You can try this using different values. Now let us look at the other sequential circuit wherein we'll use two D flip-flops. So in this example, you can see you have X and Y as two inputs. You need two D flip-flops. So this is a sequential circuit using two D flip-flops A and B with an input as X and output as Y. Okay. So let Q of A be the present state corresponding to a D flip-flop, and Q of B as a present state corresponding to other flip-flop. Similarly, these are the next state. This is a table that is given to you. Now you have Y as an output. So let us find what is Y in terms of X, Q of A, Q of T, Q of A of T, and all. As we are supposed to use D flip-flop, let us introduce D in the excitation table, and from the D flip-flop excitation table, we know that D is equal to Q of T plus 1. So you will see that D of A will have the truth value similar to that of Q of A at T plus 1. That is the values at the next level, at the next state. Similarly, for D of B, the value will be similar to the values at the next state. The expressions for dA, dB, and Y can be obtained by considering them as a function of QA, QB, and Y, and giving a truth table as an input and logisim. So let us build a circuit. Now, we need two D flip-flop. So let us find what is dA in terms of QA, QB, and X. Y is our output. So we need to find dA, dB, and Y as a function of X, Q, and Q of QB. So making a K-map, you'll get Y as what are the see the values of Y and accordingly insert them in the K-map with the inputs as X, Q of A and Q of B. You'll get y equal to this expression, which is x QB bar, x bar QB bar, x bar QA plus QA QB bar. Similarly, get the expression for DA, which is for the first flip-flop. You'll get QA bar dot QB plus QA QB bar, which is nothing but XOR again. XOR of QA and QB. Similarly for DB, insert these values in the K map and you'll find the and pair, just pair this accordingly and you'll get this equations. DB will be equal to x prime QA plus x QB. Now let us make a circuit out of this. So we need two flip-flops. From the memory drop-down box, take 2D flip-flop. And place it on your screen. Let's say this is A flip-flop, A, and this is B. Now what is DA? It is equal to QA bar dot QB plus QA dot QB bar. But what is QA? We need to take feedback. We have input as X. So let this be X. See, DA is XOR of QA and QB. So we'll use XOR gate with QA as one of its input. And QB as its other input. And this is equal to DA. Now let us see what is DB. DB is X prime and it is AND with QA plus X AND with QB. So we need X naught, X prime. We need two AND gates and one OR gate. Two AND gates between X prime and QA and one between X and QB and OR gate between these two things. Now, what is the input for first AND gate? It is X prime QA. Let's similarly for the next AND gate, the inputs are X and QB. See, this is QB, right? This wire is coming from QB. So we'll just put the connection over here. And the input for this OR gate will be the output from this two AND gates. And this will be input to the second D flip-flop. Yeah, now we are almost done. Let's put a clock. Place a clock somewhere. Now we have one more output as Y, which, like, what is this? This is nothing but it is an AND between X bar and QB bar, X bar and QA, QA and QB bar, and or between this. Now let us make this in logisim. We need 3 AND gates. And one OR gate. So what is the input to the first AND gate? It is X bar and QB bar. So we know that this is QB bar. And X bar. For the second AND gate, inputs are X bar and QA. So just extend this. and this is QA. So take an input from here. Yeah. The input to the last AND gate is QA and QB bar. So QA clear? And these are the inputs to this. We need to change number of inputs to 3. And finally, this is equal to y. Let us give an output pin. Yeah, so we are done with the circuit. Now we can change the values of x and y and check the values of y. Is the circuit clear to everyone? Were you able to follow the circuit in logisim? Hello, is it clear to you guys? Any doubts? So you can change the inputs and see for the output. This is how the circuit will look. So we have basically built a sequential circuit using 2D flip-flops, wherein we were provided with the characteristic table. Yeah, so this is it for today. Hope you enjoyed the today's session.